It is the middle of the night. No moon, no streetlights. To your eyes, the field is a wall of black. But look through this device and the same field glows. Fences, footprints, a fox standing still at the tree line. Nothing here made new light. The night was never truly empty. We simply could not see what was already there. So let us slice one of these tubes open and follow a single grain of light all the way through. Even on the blackest night, light is still falling. Starlight. The faint glow of the sky itself. A trace of infrared we cannot feel on our skin. The real trouble is amount. Your eye needs a certain number of light particles, called photons, before it registers anything at all. On a dark night, far too few of them arrive. So the scene is not truly black, it is only too dim. Night vision does not invent light. It takes the little that exists and makes it count. It begins with the front lens, wide and curved like a hungry eye. A bigger opening catches far more photons than your pupil ever could. The lens bends every incoming ray and funnels them onto a small, flat target at the back of the tube. Think of a bucket left out in a light rain. Widen the mouth of the bucket and you collect more drops in the very same minute. Here the drops are photons, and the target waiting for them is about to perform a quiet trick. That target is a thin coating called the photocathode. When a photon strikes it, the coating does something strange. It absorbs the light and spits out a tiny particle of electricity in its place, an electron. One photon in, one electron out. The picture you could not see has now been copied into a pattern of electrons, floating just behind the lens. Same image, a different messenger. And electrons, unlike light, can be pushed, pulled, and multiplied. That difference is the whole reason this device works. These electrons now travel through a sealed tube with the air sucked out. A vacuum, stray air molecules would scatter them and smear the picture, so the tube is emptied to almost nothing. Across this empty space sits a voltage, an electrical slope. The freed electrons feel that slope and accelerate, sliding forward in perfect formation, each one holding its place in the pattern. The faint image, now made entirely of electricity, drifts steadily toward the heart of the device, where it will be made strong. Next, they meet a wafer no thicker than a coin, drilled with millions of microscopic channels. Picture a honeycomb of tiny glass straws, each one narrower than a single hair. Every electron falls into a channel and strikes the wall on its way down. That collision is the secret. One electron hitting the glass knocks several more loose. Those fly deeper, hit the wall again, and knock loose even more. A single quiet arrival, in the space of a few millimeters, becomes a small crowd. Down the length of each tiny channel, the strikes repeat again and again. 2 become 4, 4 become 16. By the time the electrons reach the far side, one original has become many thousands. This is the amplifier at work. It does not add a single photon of real light to the scene. It simply takes the faint electrical copy and multiplies it over and over until a whisper becomes a shout. The dim picture that entered is now blazing, carried by a flood of electrons. This electron storm slams into the final surface, a screen coated with phosphor. Phosphor is a material that glows when struck by electrons, the same trick that lit up old television tubes. Each electron landing makes a tiny point of light flare up, and because the electrons held their formation the whole way through the tube, the glowing points rebuild the original picture, line for line, dot for dot. The scene you could not see has returned as light, only now it is bright enough to read. And it returns in green, always green. There is a reason for that. The human eye is more sensitive to green than to any other color, so a green picture looks brighter and shows finer detail for the same amount of energy. The phosphor is chosen to glow in exactly that shade. Designers could have picked white, but green lets you stare for hours with far less strain, and your eye catches the faintest shapes hidden inside it. The color is a careful decision, not an accident. A final lens, the eyepiece, magnifies that green picture and delivers it straight to your eye. The loop is complete. Real light went in the front, and a far brighter copy comes out the back in real time, with almost no delay. When even starlight runs out, many devices switch on their own infrared lamp, a glow that is invisible to us but perfectly plain to the photocathode. The device quietly lights the scene with a color no human eye can see, then shows you the result. It is not magic, and it does have rules. Point it at a bright porch light, and the channels flood with electrons. The image blooms into a white smear that hides everything around it. And in total darkness, with no light at all and no infrared lamp running, even this device sees nothing because it can only amplify what already exists. It is a magnifier of light, never a maker of it. But give it just a few stray photons and it will hand you the whole night. So follow one grain of light through the entire machine. The wide front lens gathers it. The photocathode turns it into an electron. The vacuum and the voltage speed that electron along. The microchannel plate multiplies it into many thousands. The phosphor screen turns the crowd back into glowing points of light. The eyepiece hands the finished picture to your eye, painted in green. Gather, convert, accelerate, multiply, glow. 6 quiet steps, all finished before you even noticed the dark was ever there. The night, it turns out, was never empty. It was only quiet. A handful of photons, caught and copied and amplified, was always enough to draw the world back into view. So the next time the lights go out, remember that the scene does not vanish. It simply waits for something patient enough to gather what little light remains and to make it count. That is the trick hidden inside the dark. This was the Cutaway.